there. Today we're going to talk about energy and electromagnetic waves. One thing we all know is that waves carry energy. That includes electromagnetic waves carry energy. Energy density represented with a lowercase u is energy per unit volume. In empty space, for an electromagnetic wave, the energy density looks like this. U equals 1/2 epsilon naught E squared. That would be the energy density due to the electric field, plus 1/2 mu naught B squared. And that would be the energy density due to the magnetic field. If we do some substituting, we know that B is equal to E over C. We also know that C is equal to 1/the square root of epsilon naught mu naught. I'm not going to show you all of that, but if you take advantage of these two pieces of information, you can replace B, and this will actually come out to be 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared. And what we find is this quantity is exactly equal to this quantity. That makes sense. So the electric field and the magnetic field each contribute an equal amount of energy to the energy density. You can, of course, add those together, and you get that this is epsilon naught E squared. And of course, it has units. It will be in joules per cubic meter. So it's one way we talk about or describe the amount of energy in a particular electromagnetic field that's based simply on the square of the amplitude of the electric field. Another way that we often talk about energy is intensity. The intensity of an electromagnetic wave is the average power per unit area. So I is simply equal to the power divided by the area. It's going to have units. Power, of course, is watts. That's going to be watts per meter squared. So an intensity is the amount of watt. Remember, power is the amount of energy per second. So it's energy per second over a square meter. Again, if we substitute in some of what we know as descriptions for power, the book does all of the derivation. I don't want to go spend that much video time just doing algebra. We get a formula that looks like this. I is equal to 1/2 epsilon naught C times E max squared. So that's the maximum amplitude squared. Or another formula which has to do with replacing the fact that C times E is B max, just doing a little bit more of that substitution, and we can get that the intensity is the maximum value of E times the maximum value of B over 2 mu naught. So two formulas, both really easy to use. It really just depends on what information you have available as to which one of these formulas you want to use. All right, let's look at an example. Again, if I go too fast, simply pause the video, take your notes, and then start me talking again. So our example says that we have a laser cutter has a maximum electric field in E max that's 2.76 times 10 to the 5th volt per meter. That's the maximum electric field over an area of 2.00 square millimeters. So over this very small point of where I think of like a laser point, a small dot where that laser has that power. They want me to find a lot of things, so we'll just go one by one. The first thing they want me to find is the maximum magnetic field. Okay. We know that the maximum magnetic field is just the maximum electric field divided by C. So this is going to be 2.76 times 10 to the 5th over 3.00 times 10 to the 8th. That comes out to be 9.20 times 10 to the negative 4 Tesla. Once again, let me just remind you that the magnitude of this magnetic field seems really small. This is a very small number compared to this maximum electric field. But both of those have the same energy density. They both contribute equal amounts of energy. So the fact that one is large and one is small is just about the size of the units, not that one is more powerful than the other. Okay, the second thing they want us to be able to find is the maximum energy density. Well, we know energy density is given by U equals epsilon naught E squared. So to get the maximum, we just use the maximum value for E. So that is 8.85 times 10 to the negative 12. That's epsilon naught. You can look it up if you don't remember it. E max is 2.76 times 10 to the 5th. That gives us a maximum energy density of 0.674 joules per cubic meter. Energy density tells us what the energy is per unit of volume. Okay. Part C asks me to find the intensity. Our intensity formula, they had a couple of them, but one of them was 1/2 epsilon naught C E max squared. We know all of those quantities, so that seems like a good choice. 1/2 epsilon naught is 8.85 times 10 to the negative 12. Speed of light is 3 times 10 to the 8th. E is given as 2.76 times 10 to the 5th. And it's E squared, so we do need to square it. I know you can't see me, but you can see the picture. 1/2 epsilon naught C E squared. That's just a punching in a bunch of numbers. And I get that the intensity is 1.01 times 10 to the 8th watts per meter squared. There's our unit. Okay. They ask us to find one more thing, and that is the power. Okay. Average power is based on intensity. I'm going to leave that intensity because we do want that value. We're going to just erase this kind of in the middle here. Okay, part D says, what's the power? Well, we can remember that intensity is equal to the power over the area. So the power is equal to the intensity times the area. Intensity is 1.01 times 10 to the 8th watts per meter squared. And the area, it's given in millimeters. I'm going to have to fix that millimeter. It's 2.00 square millimeters. But I'm going to have to do 1 meter is 1,000 millimeters. And I'm going to have to square that to change that to square meters instead. That gives me a power of 202 watts. Okay. I don't think you'll have any trouble with using those formulas for energy density or for power or intensity. Just pay attention. I think you'll be just fine on those. Let's go ahead and talk just a little bit about some of the information that's in the next section, which is section 23.6 over the nature of light. This is a section you should read because the material is material you can simply understand by reading. It's not about formulas. But one of the ideas they talk about is the fact that for a very long time, up until about the time of Isaac Newton, everybody was very confident that light was particles. They thought it was a beam of particles. They called corpuscles. Corpuscles is just an old-fashioned word for a particle. But then, about that time, they started realizing that, hey, light has a lot of wave properties. In fact, we've described it in terms of wave properties, wavelengths and frequencies. It has interference patterns and diffraction patterns. And they said, well, it's not particles, it's a wave. And that seemed to be the solution until 1905, and Einstein used the idea that light was particles or a quantum of light when he solved the problem of the photoelectric effect. So first it's a particle, then it's a wave, then it's a particle again, and then finally quantum mechanics came along and said, hey, it can be both. We have what we call wave-particle duality. Really kind of hard to understand, but a really important idea. Another really important idea that they talk about in this chapter, or in this section, is the idea that all light, and by light I don't mean just visible light, I mean radio waves and microwaves and x-rays, all electromagnetic radiation is a result of an accelerated electric charge. Everything you know of actually emits thermal radiation or heat, simply due to the fact that the particles, the molecules are vibrating. Now, they don't emit enough thermal heat to give off visible light. Now, a few things do. If matter gets so hot that it gives up enough at the right frequency, then it starts to glow like a light bulb filament or a candle wick. Okay? But all light is really the result of electric charges and accelerate, or when I say all light, I mean electromagnetic radiation, accelerated electric charge. Okay. And before we move into the next section, in the next video, the other thing that was kind of talked about a little bit in 23.6 are the idea of wave fronts and rays. If I have a pond and I drop a rock in the middle of the pond, it will set up waves that move out in concentric circles. We can think of each of these being a crest. And this distance from here to here would be a wavelength each time. Well, it turns out that if you have a source of light, like a light bulb or the sun, it does the same thing. It sends out waves of light in all directions. We call these wave fronts, as opposed to maybe crests, because physically they don't quite look like a crest. But these would be wave fronts. They'd be concentric spheres that move out from the center of a light source. If we draw lines that are perpendicular everywhere, think maybe this is like the sun here. These would be rays. These would be wave fronts. Treating light as a ray is going to help us solve a lot of problems in the next few sections. So we often think of light traveling in straight lines as rays. If we have parallel rays, what we find is our wave fronts look like this. It might not occur to you, but the sun is actually a really excellent source of light rays that are almost perfectly parallel. And you go, well, gee, the sun looks like this, Miss Hughes. These rays are not parallel at all. But what we have to remember is we're really, really far away from the sun. So all of the rays that hit our little teeny tiny planet Earth over here, better move Earth up a little so I hit it. There we go. Those rays are all perfectly parallel. There's very little variation in angle. So anytime you're outside, all of the rays of sunlight are for practical purposes perfectly parallel to one another. And we can use that in some future problem solving. Okay, that concludes this lesson over energy. I will see you in the next lesson.